I'm Chris Bidwell. I'm a network engineer. I work in finance, have done for about 15 years or so now, and I've been coming to SharkFest for a number of years, since about 2013, I think. Love it here, love the crowd, love the people, and I hope you do too, and continue to come back and present. That's how I got here. So today I'm going to try and run through a few things that I find interesting when I'm looking at PCAPs. So I'm going to try and show you all of the sort of things that draws my eye. Hopefully I'll do this in about 60 minutes and have a few minutes for Q&A later, but no promises. So if I'm running late, do give me a wave. I'm not going to show you everything that I do, and because obviously in the interest of time, it's awkward, right? And you know, it depends on what we're dealing with. So I'm going to try and make sure that this is just kind of tailored for the kind of things that I would look at when opening a PCAP for the first time with no real idea of what's going on, or a very, very vague description. You know, contact your network administrator. We've all seen the error message, and we inevitably get a call for various bits and pieces that have nothing to do with us, right? So sometimes it's something that I know about, sometimes it's not. When I'm opening a PCAP, I'm trying to just essentially get a feel for it. I want to get glance level familiar, as I've referred to it here, in the sense that I want to be able to glance at it, get a shallow feel for what kind of things are there, what things I might need to dig into. It's too early in the process to go digging right down into the detail for absolutely everything we want, but you need to see what's there in order to understand whether or not you're going to have something to look at or need to go back and ask more questions. So we'll take a look at a few PCAPs, try and get glance level familiar with them, and then try and build a picture of our observations. I'll try and point out some of the weird and wonderful clues that I see in there, and some of the distractions that I see too. So hopefully that resonates. The last part here in terms of my go-to graph for performance queries, I'm going to do live, so it might be a complete disaster. So we'll see how that goes. I was looking for a particular PCAP I really wanted to use from one of the previous capture challenges. If anybody has boyscout.pcap handy, then I might open that later. But that was an interesting one. I'm going to try not to reinvent the wheel here and make like statements that I think are, you know, too definitive. And equally, I want to encourage you to make sure that you pay attention to all of the other presenters here. You know, everybody's got a different way of doing things. They'll give you all kinds of nuance that you wouldn't have thought of. Just pay attention to the weird stuff in the details, right? So all of the PCAPs we're going to look at have actually come from the Wireshark website's sample captures page. So they're ethically sourced in that respect. The industry that I work in, it would be impractical for me to try and get captures here to show you what's there. But these ones here give us a fairly good idea of several different protocols that are in use, and give us a good way to kind of get familiar with what you might see on the LAN. So hopefully you recognize all of these protocols that I've listed here. Looking at them in isolation like this, I think, makes it a little easier to sort of understand what we're going to look at overall in terms of building a bigger picture. So it just means that we've got a little less cruft in front of us. We can focus on one thing at a time. I don't have to do any recarving or too much filtering. So these are nice, discrete examples. By being here, you have inadvertently accepted the terms and conditions. This is one of many approaches, right? This is how I do it. It's not going to be the same as the way you do it. You'll hopefully find something interesting and valuable in there. I'd like to think that I'm methodical, but usually not. I'd like to think I'm consistent, and sometimes I am. I really don't make that much use of custom profiles in terms of like how I work with Wireshark. Most of the environments that I work in, I don't get the luxury of being able to load up my own customizations. Like often I'm either shoulder surfing another engineer who's got his own setup or her own setup that they want to deal with. But frequently I'm dropped into an environment where it's just not practical to get external access to things. I'm sure some of you are familiar with the kind of environments I'm talking about. I will customize the UI, but only in the specific areas that I really care about. For most things, I'll just leave it as default. I might hide a couple of columns. I'll change a couple of things just to make it slightly easier, but hopefully they're fairly straightforward and trivial to kind of re-implement yourself. I'm going to make mistakes. I've done it before. I'll do it again, and I suspect you have too, and so please be kind if you notice that I am screwing up. I don't want to spend more time troubleshooting Wireshark than troubleshooting the network problem, which is one of the reasons why I've kind of got to a point where I'm happy just using a lot of the defaults and understanding the specific things that I want to tweak for the job at hand. Many of the defaults are actually really, really good for this, and especially now, Wireshark 4.0 has actually invalidated a good chunk of my talk in terms of having adopted many of the customizations that I would have presented anyway. So if you've already seen the difference between Wireshark 3.x and prior and Wireshark 4, for instance, like the panel layout, etc., I think that these are good changes. I know that some of them are a little contentious, and not everybody does it that way, but here's how I do it, and remember, your mileage may vary, yeah? I'll use Wireshark 4.x when I'm actually opening stuff. I think it's 4.01 currently. I think I've upgraded. Please be gentle if I make a mistake or fumble with the interface, and if I can remember, I'll try and point out the changes that I've made in my approach as a result of Wireshark 4.0, but fortunately, it's mostly just a quicker path to entry. So, in our line of work as a network engineer, I think that there's a couple of pieces of essential scripture. Like my Bible is TCP/IP Illustrated Volume 1 by Stevens. I think most of us have got a well-thumbed copy or an exceptionally well-opened ebook or similar. And I mean, you can see here, like the quote that I've included from Vint Cerf there. You know, it's a fabulous book. It really does go through an awful lot of detail. But it was last updated in 2011. And there's been a fair few changes in the way that we do things in the last 11 years. And one of those is this other piece, the TCP RFC. RFC 9293 was released in August. Yeah, August 2022 became standard track. And as you doubtless have read and heard from others, you know, essentially all it's doing is pulling together a bunch of disparate RFCs, trying to make it a little easier for us to get where we're going without having to bounce backward and forward between, what was it, like 7 documents in order to figure it out. I've heard 20, but I'm sure it was fewer than that. I'm sure you've heard "it depends" come out quite a few times from some of the presenters. It's certainly the thing that I think I utter the most when answering questions about networking and when people have something that they're interested in and want to know if it's normal or not. Hopefully, I don't say it too many times today, but being as I've kind of planned this. I think that in the lower layers of the OSI model, you know, layer 1, layer 2, layer 3, obviously. We don't see very much of layer 1, do we? But layer 2 and layer 3, we get a really good idea, obviously, of topology, how the various things are connected together, what essentially is there, what's communicating, squawking away. In the higher layers from, well, arguably 3, but 4 through 7, you know, we're looking at application detail. It's whatever is going on in our environment that is custom to us. You know, this is not necessarily going to be the same everywhere, and maybe this is where the more interesting stuff is. For me, usually it's in the lower layers. I prefer to be deeper and closer to the wire, I think. I find it really, really confusing when I'm dealing with large PCAPs with a lot of interleaved sessions, right? And the real world is such that nobody stops and sits and speaks patiently one person at a time anymore, right? And especially not on a full duplex network. At the bit rates that we're dealing with, it can be common to have like a great deal of number of packets within like the space of a second. And some PCAPs you might look at and think that this has been going on for hours, but it's seconds. I find it much, much simpler when we start to, you know, looking at a specific conversation, and you all should too, I suspect, like apply conversation filters, right? But do it judiciously. Don't be too early with your filtering, and don't sort of leave it in place for too long. Be careful with where you're at. Kind of remember what your context is. It can be very, very easy to kind of get lost in that stuff. I make a little bit of use of coloring conversations, which is quite handy when you just want to be able to highlight a particular thing, or you want to be able to differentiate two particular sessions. But I'm not really going to use it today. And I will go through a follow stream example a little later, which I personally think is not the most effective way of troubleshooting an application problem, but for a plain text protocol, works pretty well. FTP, HTTP, SMTP. I like the ability to kind of just get a good idea of where this thing is going really, really quickly. The process is going to be, you know, you find normal. You need to figure out what exactly is normal on your network before you're going to be able to identify what is not normal, right? I mean, people say capture a baseline, know your baseline. It's harder than it sounds. I've spent a good number of years trying to have a baseline, and the best I can do really with the pace that everything changes is knowing what I think is fairly normal and weird. So, you know, it's easier the more you see. Just keep practicing. Keep at this. And like I said before, you'll be wrong, so be humble and be conservative. You know, it's very easy to ruin one's reputation by blaming something a little too early. So if you're not totally sure, make sure you raise some doubt, or ask a colleague, ask friends, ask people that you trust. And sometimes ask people that have got no idea what's going on in your world. Sometimes it takes a blank canvas to really figure out, like, what are the questions you forgot to ask. So be prepared to have conversations with people. Down here, I've suggested peer review kind of works, right? I find that, as per Randall in his XKCD comic and Cunningham's Law, the quickest way to the right answer is not to ask the question. It's to point out your own wrong answer. Somebody will jump down your throat quick enough to point out where you have made a mistake. Happens often in my life. So I think this is the last time that the URL for the PCAPs is going to be visible. So if you haven't already done it, grab it now or snap a picture or whatever. So I'm sure like this sounds familiar with some of you people in terms of how like your work goes, in terms of what people bring up to you. Often it's an emergency. It's always an emergency. Everything's a priority. And in my line of work, it's frequently something along the lines of latency being observed on connections and trying to figure out who's at fault. Is it us? Is it a counterparty? Who essentially is slowing down the rate at which anybody can do their job. There's lots of finger pointing and, yeah, well, get to the PCAPs. They don't lie, right? The packets don't lie. So get your evidence. Sometimes it's a PCAP, well formatted, well captured. And sometimes it's a janky screenshot. I'm sure you've all had a Word doc delivered to you with a screenshot of Wireshark in it at some stage. Maybe it's just CLI output of TCP dump. Don't be afraid to go back and ask for people to do things again if you really need to. Like, it's at the end of the day, it's not your fault if the evidence that you supplied isn't good enough or that you actually can't do anything with. So be confident enough to make sure that you're digging into the right things. But I'll show you how I kind of get a feel for whether or not there's enough information there for me with what I think is going on. My first clues are things like the file name, for instance. Like, who's captured this? Where have they put it? Like, if there's something in there that includes a timestamp, maybe that's useful and relevant information. But maybe it's a lie. File system metadata. Like, if things have been copied around from one file system to another, that doesn't necessarily reflect the real creation date and the real modification dates. So, be careful with what you assume. Tip here in terms of making sure that you're able to kind of get back to where you're supposed to be when inevitably you get lost. Make a read-only copy of whatever you supplied. Keep an archive of it. Have it sat there so that should you delete the wrong thing, manage to recarve a file and save it over the original and forget that you actually don't have another copy. If you've got an archive there that's marked read-only, that you're working in a separate copy, worst case, you've just got to redo the work that you've done, but you're already in a good position. If you need to go back and ask the source for the file again because you overwrote it in their file system, that's probably not a great place. File and frame comments, they belong in the working copy, right? Don't be messing around with the original too hard. If you need to supply that back to somebody, then that's easy enough to do. But if you are, really consider whether or not you should be anonymizing any of the data in there. Part of what the point of this talk is and per Jasper's mantra when he developed Trace Wrangler, is there's all kinds of stuff in the protocols that we're looking at that gives away really weird details that might be sensitive. And his philosophy there is that if you don't understand it, you don't know how to interpret it, it doesn't belong there. Cut it out. If there's a protocol that you don't understand, maybe there's something really sensitive in there. Maybe it's just a ROT13 encryption that's been applied to it, and maybe this is giving away some trade secrets or something. So be careful. Be paranoid. Just because you're paranoid doesn't mean they're not out to get you. If you've got your pen and paper ready, let's take a look. So, first things I do, as I said before, I'll take a quick look at the file name. I'll take a look at the size. I'll try and get an idea of what exactly it is that I'm looking at. I've no idea really how long it's going to take me from the size of a PCAP. It could be kilobytes and have absolutely tons of packets in it. Because it was gzip, perhaps. Perhaps it was snapped at 64 bytes, and that makes it very compressible, obviously. But maybe it's a huge file, and it actually all, maybe it was a 10 gig link or a 100 gig link or a 400 gig link that you were capturing, and seconds worth of data has exploded into hundreds of gigs in some cases. So be mindful that these clues are not necessarily valid. These are things that could be interesting, but you need to kind of dig a little bit deeper. As I mentioned here, the first change that I would normally make in the interface is to go ahead and adjust the panel layout for the UI, but I don't have to do this now, so that's nice. I hope that you also like this view because you're going to be seeing it for the rest of the session. But I personally prefer to have, top 2/3 of the screen occupied by the packet list. That's where the majority of my work is going to be done. And the packet details are like fairly large over in the bottom left corner, exactly per the defaults now. And I'll spend quite a bit of time in there. But the hex view, while I'm not often using it, sometimes it's incredibly valuable to just spot that weird detail, especially if you're scrolling through a list of packets and trying to spot something like, is this one identical to the one before it? sometimes it's very easy to see when you're just glancing at the hex view. Obviously, depends how much data you've got. In my UI, when I'm modifying things like columns, I try and make sure that I use short names, just so that I can also use the automatic column resize and not have the column name blow it all out, and actually use the values as the thing that defines how big the display is going to be. But I find that delta time from the displayed packet is one of the most valuable fields that you could add as a column. You'll see me add various things as a column and turn them off as I'm going through some of these captures that I'll show you. I don't do a good job of cleaning up, so if you are glancing in my column list, don't be horrified. Filtering obviously can, as I mentioned before, when we're filtering to look at a PCAP in terms of what we're actually analysing ourselves, if we are not careful about remembering what we've done, or the number of times I sort by a column and forget about it and realize that I'm not following the packets in the order that they are actually sent out, it's ridiculous. But we can often get a really good idea as to whether or not somebody's done a lot of filtering just by looking at what's there. Like if there's a lot of layer 2 traffic in there, like Ethernet, non-IP traffic, there's a really good chance that there's not very much filtering been applied. This is probably going to be an interesting capture. This is something that, especially if there's no filtering whatsoever, you probably got everything, unless something's hidden. But if there's no layer 2 traffic, be aware. Probably somebody has been very, very careful with what they chose to share you. Okay, so once I've got a packet capture open and I've started to glance around it, one of the things I'm going to do is I'm going to pick a conversation, just at random more or less. It'll probably be the first, but it might be the more interesting one in terms of like number of packets that appear in it. And I'm going to click around. I'm just going to click it. Various values that are in the display tree for the protocol tree, see whether or not values look right. Do I need to care about a bunch of things like checksums and the frame length? Like, are these things right generally? Are there any frames that are in here that have got bad checksums, and what kind of thing might that indicate? Things like VLAN tags can be quite interesting when you dig into the details of what VLAN tags get used for. Can be used for pushing class of service information instead of VLAN data. And similarly, DSCP is something that I've overlooked numerous times in the past when troubleshooting things like link loss issues. Well, it turns out QoS was the cause of the problem. DSCP markings make a difference. But I'm not going to look at too many of those today either. The slow protocols, as they're defined, I think are actually extremely interesting, especially like broadcast and discovery type protocols. LLDP is a trove if you should find it, and I think FHRPs are actually also quite interesting, first hop redundancy protocols. Oops, sorry. So at the layer 3 part of this, when we're dealing with IP and you're looking at things like fragmentation, have we got MTU issues or disparities? Are we fragmenting? And if we're not fragmenting, as I'm sure you've heard before, the ID value can be incredibly helpful here to figure out where exactly we are, what this system is. There are various heuristics you can apply to determine what operating system you're actually facing off against based on how it deals with the IP ID. If you've got all of the traffic coming out of a particular interface, potentially you can see that IP IDs increase monotonically. If you're missing a particular ID, is that indicating that it was lost? Is it indicating that your capture failed to get it because perhaps it overran a buffer? If they're completely random, as things like OpenBSD, is it NetBSD, would apply, then this isn't going to be of any help whatsoever. It's simply a useful thing for identifying where fragments are going to coexist. Out of order IDs in this case also can be very interesting and indicate things like path asymmetry. If you know full well that you have a system that is sending out monotonically increasing IP IDs, and yet you're seeing them appear in a random order, well, maybe Wireshark's right in that the previous segment was not captured at that particular time because you've got an asymmetric path somewhere that's causing something to be delivered later than others. In the handshake and things like TCP, there's some other really valuable information. Calculated these days is the initial RTT, and it's wonderful that it's there, done by default now, but the three-way handshake for TCP is one of the most reliable places for you to figure out what the initial RTT is, because it's the quickest part of accepting a connection, usually. Assuming that you've actually already got reachability to the thing and the system isn't waking up or isn't under load, but you'll obviously get a good idea of what the RTT for the connection is going to be overall, and from looking at the IRTT. And if you miss the three-way handshake, you miss values like windowing, window scaling options that are going to be enabled, and indeed an initial RTT calculation. A couple of other things that might be interesting here: timestamps. Like what might timestamps imply? At some time, it might have been that timestamps were implying that you were trying to measure data, measure the actual time of a packet traversing the network, but these days it's frequently just used for detecting wraparound, pause, protection against wraparound sequence numbers, which in high bandwidth networks, as many of us are dealing with on a day-to-day basis, this is something that we need to care about in order to figure out, have we just had a delayed packet somewhere, or is there real garbage? And speaking of garbage, don't forget that sometimes things really do fail. I've seen many captures, particularly from things like failing taps, where I've had a surprising amount of corruption appear in the trace and thought, there's some random protocol here I don't understand. No, it was bad DRAM in an aggregating tap. Hardware does fail. But equally, it could be that you've got an unexpected application. There's various tools and toys that will hide. Obfuscation is a thing. People will want to try and have their thing not look interesting so that people don't go looking for it, and it drags my attention, certainly. So let's start out now with an actual PCAP. So this one is, the URL up there is where it's obtained from. It's all my source. This particular capture file is going to be looking at a couple of BGP sessions, and we're going to dig into some detail and then hopefully draw a picture as to what we might be dealing with. Right. So BGP. Border Gateway Protocol. I mean, I'm sure this is not a BGP class, and you could pay Cisco a great deal of money to go and learn about it for a week at a time if you wanted to. I'm just going to glance into a couple of details that I think are interesting here in terms of the kind of things you can pick out from just observing traffic on the wire. So this capture here is of 4 IPs, as we'll see. You can see there in the list if you're glancing through them yourself. 50.1, 50.2, 51.1, 51.2. I promise they're the only ones that appear as we glance through this particular PCAP. There's a lot of red here, isn't there? Is this a problem? It depends. So let's figure out why this is red in a second. Okay, and we've got 155 frames. I think, what is it, 4 are not, 4 frames are not marked as being a problem per the coloring rules here. So how do we figure out whether or not this is a legitimate problem? Should this be as alarming as it looks? So I'm sure you know how to do this. We'll go and grab the coloring rules from the interface. I don't know how to make this any bigger, so you'll have to squint, I suspect. This one here is going to be the thing that's responsible. This is the style that this particular thing is being displayed in the vast majority. We've got the sort of white-grey text on the red background. And here's the coloring rule that applies to this. And we can see that it's TTL lower unexpected. Is that a problem? It could be. It could be a problem if you're dealing with, say, multicast traffic that has reached TTL1 but is clearly not at its destination yet. But if, in this case, we've actually got quite a lot of, it's BGP, what we've got here, TTL might well be expected to be low. There's a security feature to limit the maximum TTL that we're going to accept from or transmit with, so that a BGP peer can't be tricked into communicating with something that's further away than it expects. So this rule here is showing us that essentially I don't care why these particular messages are read. And how do I know that? Because we're going to go in here and we're going to take a look at the time to live and see that the TTL there is set to 1. If I sort now by the TTL, which you can see there is the column name, up at the top here, all of these messages are TTL1. And this might be a problem in a different protocol, but in this, it's not. I just really don't care that TTL is 1. It surprises me that I see TTL 64 here on these packets, and it surprises me that these are 255. And that could be interesting. That might be something that I care about. Maybe it indicates that these hosts are running a different version of the software. Maybe they're running a different operating system. Maybe there's some customization that was made to something whereby the default TTL that is being used for transmit has been customized for whatever reason. But I don't think this is necessarily very interesting right now. Certainly it doesn't seem like there's anything wrong in the capture in terms of seeing anything like out of order messages or packets lost. So I think everything looks like it works here quite well. I'd say it's a red herring. Anyway, so I think we're clearly on the same network. We've got TTL1 here in all of these messages. The IP pairs that we're dealing with are clearly in the same subnet. Everything looks good. I mean, okay, all 4 of these could be in the same subnet, but you know, they're not, as we'll see when we look through. Okay, I'm going to sort now by frame number again, so that I don't get too lost. And now as I scroll through here, what we've essentially got, we've got a connection attempt here that's been rejected. Another connection attempt that's been rejected. And this is persisting. And then finally here, you can see on the left here, this is another wonderful feature that was added to be able to see whereabouts the whole sort of conversation or the related packets sit, if you use it right, and makes it quite a lot easier for me to see that this is an interesting conversation. So this thing actually has a bunch of packets in it. It seems to have actually been established. And we can see, when we get through the 3-way handshake, we've got a BGP open message. Let's just collapse the IP, and now I'm going to go ahead. I'm going to expand all of these subtrees in one go. I'm going to scan through this particular set of details just to see if anything jumps out at me. Conversation completeness, if you've not noticed this before, this is actually something that's really interesting too, but it's for another session entirely. We can see sequence numbers, push, ACK, okay, push, could be interesting. Our checksum's unverified. Let's just double check that. So if you're familiar with the quick way to do this these days, you can right-click on a particular value here, specify or hover over the protocol preferences here, and I'm going to validate the TCP checksum if possible. And it's good. Okay, great. So maybe I don't need to worry about that too much. We've got timestamps enabled. There's our initial RTT calculated that I mentioned earlier. If you Google for that and some of the presenters' names, you'll find some enlightening documentation about how that works and why we can rely on it to kind of figure out, well, how the network's performing, but also using the initial RTT and some other like the delta time essentially, we can try and figure out whereabouts we are compared with in sort of the network. Like where have we actually captured this traffic? What are we closest to? Are we closest to the server side, the client side? Are we somewhere in the middle? Are we way off? Were all these packets generated on the same host, potentially? That might be interesting too. All right, so in the BGP open message, a few protocol-specific things. Again, I'm not going to go through all the BGP things, but explain subtrees, there we go. There's various information here that's quite handy to take a look at, and things that we're going to be able to see, like how carefully have things been designed here? Like, are we just running defaults? Things like timer messages, timer values here, like a whole timer of 180 seconds. 180 seconds. It's an age, no? For a BGP session. We're going to wait potentially 180 seconds before we decide that our peer might not be there anymore. That doesn't strike me as particularly performant, but it also suggests to me that this is default, because that is the default. We've got an identifier here that could be interesting. Is this the same as what we're actually dealing with? Let's just scroll up here. IP source 192.168.51.2, and down here 192.168.51.2. Okay, so the BGP router ID is the same as the IP address that the device is actually sending out this packet with. Is that interesting? Maybe. Carry on scrolling through here. Ooh. FQDN capability. This is a host name. Look, we have an Ubuntu system, apparently, Ubuntu 01. Okay, so this seems like maybe a demo that's been set up specifically to generate this kind of capture. And there's nothing else here that really grabs my attention. There's obviously various features that we can see here that are included, like the graceful restart capability. That could be very interesting in terms of what you might expect the devices to be doing when you see various behavior, and how the device actually might respond. You can kind of predict how the routing daemon is going to behave or how the router itself is going to behave in the event that the protocol is disrupted. So if we've got graceful restart, one of the goals of that is to be able to deal with, for instance, a device rebooting. We want to be able to essentially tell a neighbor to keep various information in memory, don't throw it all away, don't go through your expensive calculations again, because we'll be back in just a moment. We're just rebooting, or we're bouncing a link perhaps. So that was interesting detail in that one, but where's its peer? So 51.2 sent that particular packet, and here's the response from his neighbor. So this particular conversation, we can again glance through some of these details and see what he's doing. Like, so BGP ID here is 51.1, that's very similar to the other one. Again, source IP is 51.1. Oh, my TCP is red. Why is my TCP red? My checksum is incorrect. Could this be a problem? Well, I mean, as it says here, it could be caused by TCP checksum offload. Usually, I would expect to find a TCP checksum set of 0 if we were using offloading, rather than having a value there that looks like it could be legit, but has clearly been declared wrong. So what else might be going on here? Maybe the frame has been augmented. Maybe it's been truncated somewhere. Maybe it's been messed with by something just before it was captured. Maybe it's been messed with after it was captured. Maybe somebody's carved some data out of there. But this is interesting. I'm going to jot this down and pay attention to this in a little while. If I had pen and paper here, I would jot this down and pay attention to it soon, because I think that's interesting and worth digging into. But clearly, it's not problematic. It's not such that the packet is corrupt, because TCP seems to be working here, right? We wouldn't be having progression if either of these peers thought that the packet was genuinely corrupt when it arrived. So that checksum is probably a red herring, but it could be indicative of something interesting on our network, the way that we've captured it potentially. What else have we got here? So our TCP was red, but we were looking through the BGP, and right, so an AS number, a different AS number to what I spotted earlier. We were looking at 65100 from the other device, and this is 65100, and this is 65,000. These are all in the private range. Again, this looks like a demo that's been set up, probably. But that's confusing. Again, we're in the FQDN capability that has been defined here, and that's the same host name that we just saw a moment ago, isn't it? Ubuntu 01. So 51.2 is showing that its host name is Ubuntu 01. You can again see this here, nice and easily laid out in the hex view in the bottom right. But when we click on this message, it's the same. Is it the same host? Maybe it was cloned just to make the demo creation easier. Maybe that's interesting. Maybe it's worth bringing up with the people that raised this particular capture with you, but I think it's probably a red herring in this case. I probably don't care, although I'd also argue that's not an FQDN, is it? So where's the domain? So carry on through here and just see whether or not we've got anything else interesting. So I'm going to collapse the TCP and collapse TCP now because I don't really care about any of the details as I scroll through. This one's red again. That's red. This is fine. Ooh, update messages. What are they? That looks interesting. Okay, we've got something that's going to show us about some route information, and another one that shows us about some route information, and a summary essentially telling us that we've done nothing. We've updated something, but we haven't withdrawn any routes, and we haven't increased any by the look of it. So why don't we just have a quick glance at what details in here and see what we've got in this particular update message here. So origin as an IGP. Maybe that's interesting. Path. Okay, we've got a path of one length, one AS number, 65100. The next hop's defined. Okay, that's the same device that is sending this particular message. Okay, so this thing has a route in there and is advertising it, but that might not be the place where the route originated. This device could be rewriting its next hop and telling all of its neighbors that this is, in fact, the only thing you care about. So we can't rely on that as being particularly useful information as to where this all came from. But things like MED, multi-exit discriminator, that could be interesting if it was in use, but no values applied. Communities, that could be useful. These are going to be used for things like filtering routes. And this is one of the reasons why, while we can look at the routes that are going to be displayed here, if I open the LRI, you can see here one of the prefixes that was advertised. You might be able to, you might assume that just because a route has been advertised here, that from one peer to another, that it's going to install that, understand it, and obey it. And maybe that's true. But communities often indicate that we're going to do something special with a prefix that's been passed around. And so we can't guarantee that this is going to end up in the routing table. But maybe it will. We know that it got advertised, so that in itself is interesting. Another one here. So we have 10.30/16, 10.40/16. Whereabouts is our neighboring update? This guy is the alternative to him, isn't he? We've got other routes being advertised in the other direction. Here's our NLRIs. We have 10.20. 65,000. Next up, 51.1. Again, we can't rely on what exactly that means, but all of this is potentially interesting information. And I've jotted down a whole bunch of things here in terms of stuff that I thought was curious. Now, I'm not paying attention to the actual prefixes because it's too much detail. And we're going to get out of BGP now because, frankly, it's making my head hurt. So let's close up some of this. And I'll just double check. What are the details have we actually got here? Okay. Well, we've got a lot of conversation here from 51.1 and 51.2. Oh, the 50s have popped up again. Oh, and now we actually have a conversation from the 50s. So if you remember at the beginning of the PCAP, this was request, reject, request, reject. request, reject. But finally down here, we actually have a session open up. So we've got now essentially two BGP peers, or two peerings that have been established here between these various endpoints that we can see. So I'm going to now go and show the conversations view because I can't keep track of those IPs. We have two Ethernet layer conversations. We have two IP layer conversations. And those are the addresses we saw. And here in TCP, oh, there's quite a few, but only two that have got any amount of actual data that's been transferred. So those are going to be the interesting conversations. We looked at a couple that had several packets flowing. These are the only conversations in that capture that are interesting. The rest, 2 packets, that sounds like the SYN and the reset. Okay, nothing in the UDP. Good, okay. So let's close that up now. We're sure that I've not goofed too heavily in terms of looking at these numbers and confusing them. There's only 4 hosts here, and we saw the MAC detail, but let's just find out what exactly that is. So here, obviously, the resolved name, rather, the OUI of this MAC address has been determined to be VMware, and the source and destination are both VMware virtual machines. Same here in this other conversation. We've got another pair of VMware MAC addresses that are conversing with each other. So these are all VMs. They all look like Ubuntu. They've all got RFC 1918 addressing. I'm guessing that they're all on individual /24s. Maybe I've got something else that will show me that in a little while. Okay, so we've got a fair few bits of information there, and I think that we might have enough to start drawing a picture. So, grab this back up. So here are some of the observations that I made as we were going through there. Hopefully I said most of them out loud. The OUIs indicate we've got VMware hosts. We've got a bunch of IP addresses in there. We can validate the number of hosts using the statistics and conversations view there. And there's 3 TTLs that we see. There's a lot of 1. There's a couple of 64 and 255. Do they imply anything interesting? Maybe. Detail there in brackets as to how I actually got there. The TTL1 to me indicates that this is local traffic, not especially interesting, but also we observed that we have a couple of different AS numbers when the peers were talking, 65,000 to 65,100. So that's eBGP, an external BGP connection. And again, as I mentioned earlier, there's a security feature in BGP to prevent neighborships being established too far away from each other. So that's entirely consistent with what I might expect to see. We've got checksums invalid on the TCP layer, but only for a couple of the hosts in there. We saw that there were several good checksums. In fact, let me go back there and show you with the column. So, oops. Here I go fumbling around. TCP, we have our checksum, incorrect. I'm going to go ahead and select this one and say apply as a column. Ticks for bad checksum. That's not the way I want to look at it really, is it? How about I use that one instead? Checksum status bad. Apply as column. There we go. Hide the bad checksum. And now checksum status bad, good, bad, good, bad, good, bad, good. Quite a variety. Sort by the column. Let's look at all the bad ones together. All the sources here, 50.1, 51.1. All of these are the bad ones. And then nothing with a 2. Nothing with a 2 as a source until we get here. All of these ones are good, 50.2, 51.2. So all of the TCP checksums are bad for the hosts that originate with a .1, and all the TCP checksums are good for a host that originates with .2. So what does that indicate? Like, whereabouts might we have captured this? I reckon it's probably close to the .1s for a couple of reasons. We talked about the fact that I would expect the value of that TCP checksum to be 0 if it was going to be relying on TCP checksum offload. But something else, when I mentioned the sort of augmentation or truncation of a frame that might be relevant here, well, it could be VLAN tagging. Perhaps this thing has got a different MTU from essentially the hypervisor presenting a VNIC to a host has got a different MTU to the one that's available on the wire. If this really did traverse a wire somewhere, perhaps this thing has either had to fragment, or perhaps, in fact, it was a trunk and there was a VLAN tag added at some stage. Maybe it was then stripped out before you saw something else. Maybe that explains it. I don't know yet. If I really care about that, that's something I'm going to go and look into later, but we won't. So we can see here, I've detailed, we've got the host name, Ubuntu 01. It appears in several of the messages here. You can go and validate that it's in each of those frame numbers, 16, 18, 65, and 67. So that in itself doesn't seem particularly interesting. And we can see various routes that are included and various attributes. So what can we do with that? Well, firstly, we remember that we've made some assumptions. We're not looking at, absolutely raw data here in terms of like what the configuration is, or rather we are looking at raw data and we don't have the context of what the configuration on the router is. So maybe some of this is interesting and maybe it's not. Speak to somebody if you're curious about this, right? People are often happy to talk about it. So I'm going to fetch my crayons and draw some pictures now. But something that I struggle with is perfectionism when it comes to trying to draw a picture. I really need to kind of get over myself. So you'll see some ugly drawings that I'm happy about now. So and we're going to redraw things. Remember, like your first shot does not have to be right. You've always got another, well, maybe you don't, but I've usually got another piece of paper. I can always go again. We've got host names, we've got IPs and MACs. They're going to be interesting. If we've figured out what the client and server OSs are, maybe they're going to be relevant to stick on a drawing. In this case, we were looking at some BGP. Maybe we want to write down the prefixes that we're seeing there and the gateways that are being used. It's a bit too much detail for right now. Maybe you're already aware of some other appliances that stick in there. If there's something in the capture that sticks out to you, make a note of it. Like maybe it's something that you want to come back and dig into later. It might not seem interesting to you right now. It might seem like it was just curious, but it might stick out to an application developer. Sometimes things just don't sit right. Make a note. So here's my first ugly drawing that I did of what I thought I observed. Can you see all of that? Yeah, it's all there. Is the red easy enough to read? Well, it's too late anyway. So I'm drawing down here that I've essentially got two conversations. I've got two pairs of hosts that are communicating. We've got 50.1 and 50.2. My arrow here is indicating the direction of the connection being made, because .2 initiated the connection to .1. I've noted down the end of the MAC addresses when it comes to the host, because there wasn't enough of the MAC address that overlapped that I need to care about any more digits than 2 at a time. But now at least I can, if I'm glancing backward and forward between the PCAP and this drawing, I can at least identify, okay, so the 63, that's 50.1. 78, he's 50.2. We've determined AS numbers that are visible in those captures. And we can go ahead and add things like I've drawn in here, like frame number 62 is where the connection on this yellow diagram on the left. Frame number 62 under that arrow is indicating to me that that's where that SYN is. Again, I can just jump back into the capture, find that particular thing, and not have to go wading through everything again and reinventing the wheel essentially. Hold down timers here that I've noted, the hold down timer of 60 seconds, or hello timer, sorry, of 60 seconds and a dead timer of 180 seconds. They're defaults, they appear on both. Interesting. So I'm going to redraw that. So I actually need to go back to the PCAP to show you a detail that I skipped here, which is that I've enclosed on the left side of here that 192.168.51.1 seems to be a host that encapsulates 192.168.50.1 and 192.168.51.1. I could see that in the capture, 192.168.50.1. 192.168.51.1. If I open each of the, let's also say we want, oh, it's all BGP. I'm not going to do very well with that, am I? Don't care about the keep alives. Let's take a look at the open messages. 50.1's open message, BGP identifier, 192.168.51.1. But note that the IP address on this particular packet is 192.168.50.1. That's not the same, but it is the same as that. And here, in this particular one, if BGP was expanded, it's a keep alive, that's why there's nothing there. 51.1 in its open, there's the BGP identifier. So 51.1 and 50.1 both share a BGP identifier of 192.168.51.1. And actually we could just go ahead and look at that the other way around, but no, I don't fancy typing right now, so I'm not going to do that. Believe me that the 51.2 address appears as the router ID for in the open messages from each of those peers on the right-hand side, the 192.168.50.2 and 51.2. My squiggles here would be prefixes that I'd have jotted down if that was particularly interesting to me, but again, this isn't a BGP class as much as it feels like one right now. I've noted down here that we've got Ubuntu systems, probably, and that they're VMware Macs. On the right over here is where the good TCP checksums are, and on the left is where the bad TCP checksums are. AS numbers that I've drawn there in circles, they're interesting, and actually we could identify that both 192.168.50.1 and 51.1 are both representing themselves as AS 65,000. Oh, I've missed a zero. Deliberate mistake, I'm sure. Adding on a couple extra details that we can also see in this PCAP, some extra metadata. I find the date and time quite handy here. Like, it's interesting when this particular PCAP was captured. That's going to be something that sticks out to me or is relevant to go back to the requester. Maybe they didn't realize that they captured on the wrong date. We can see in the packets also that we actually have some interface information available to us. And so again, I'll switch back there, and right over here, 51.1, frame, interface ID, ENS39. And if we go to analyze, whereabouts does capture file information exist? The capture file properties, there we go. We can see here, two interfaces, ENS33, ENS39, and then we can go and figure out which of those interfaces had which of the addresses on it, and know a little bit more about what this system was. So we've got interface names. We also probably have a reasonable idea of what the operating system is on this. Ubuntu appears in quite a few places, doesn't it? So back to the drawing. Now, I mentioned earlier in terms of the TCP checksums that I suspect you can tell from those checksums whereabouts you were captured. And my bet is that this capture was made on 192.168.51.1 based on those bad TCP checksums. But if you look at it and decide that different, please come back and challenge me on it. So these are the kind of things that we might be using to identify whereabouts we are in this capture. And D-time there, the delta time for the display packets will help you figure out why exactly I think that those captures were done on the .1 side of those particular connections. And as I say here, there's an incorrect CRC or FCS, but only in one direction. So I'm sure you're glad to look at a different protocol now. We've got HSRP and OSPF, and I'll try and be quicker. That, we need that, and there we are. Still big enough, great. I'm going to hide the TTL for now. No, in fact I won't. I'll leave that there because we'll use it, but I don't care about the checksum status right now either. So make it a little easier to see. So scanning through this list, 23.2, 23.1. Looks like just 2 IPs. Destinations, multicast addresses. It's all kind of expected. HSRP, chatting away, we've got active and standby we can see over here, those are expected states. OSPF squawking away with hellos. Interesting. So have a quick glance at just OSPF here just to remove the HSRP, so we've got a little something less to look at. The time here, I'm using time since epoch because that's the default. That's quite handy at the moment to look at these and see that there's 10 seconds apart in these various transmissions until we get to here, and they're all from .2. So this guy's talking and the other guy doesn't, and then at 40 seconds in, he now chimes in, and another 10 seconds goes by before he chimes again. Okay. Hello packets, DB descriptions, they're going to contain some probably quite interesting information, right? And the link state updates and acknowledgements, they're also going to provide some interesting information. But in the interest of brevity, we won't go into OSPF in that much detail. I'm going to just have a look at this. That kind of, this source IP here, 23.1, and the source MAC address, all HSRP routers. This is a virtual MAC address here. That looks interesting. And there's a physical. Cisco B5. Okay, so I'm going to just take a quick look at that MAC address, that source MAC address, and apply that as a column 2. Where is that? There we go. Source MAC's back with us. And now I'm going to sort by that source MAC, just to see which values there are here. We've got a lot of ACO1, F5B5, F4AA. We can get the same view out of the, or most of the information out of the conversation view, but here we've got a good idea that there's only 3 MACs that are appearing as sources. There may well be different ones as destinations, but we probably don't care too much. It's interesting that the virtual MAC is the one that we see first from .2. Oh, it switched. You see that in the source address? 192.168.23.2 has got this source MAC of the virtual address, and now 23.1 has got the source MAC of the virtual address. And it doesn't change. Curious. So let's look at that with source sorted. Real MAC address, virtual MAC address. Oop, there's the change. Oh, no, we're not ordering by a frame number anymore. Sorry, there's the mistake. 23.1 source, 23.1 is the virtual, 23.2 physical, and then the virtual. So they both end up using the virtual at some stage. Curious. And if we maybe select this one and order by the frame number and go and look at that source MAC there. AC01's 23.2. 23.1's now the source MAC. Somewhere around here it switched over. What happened? Look at the HSRP. Around frame 23, 22. Oh! 23.2, 23.1. Coup, state listen. Okay, so we've had a new HSRP router come online and decide that it wants to be active. Now, if we carry on looking into the various protocol information for HSRP, we can see things like what state we're in, what virtual address we're using, 23.250, which is, that doesn't appear as a source here anywhere. I don't think it appears as a destination anywhere. We're only using multicast addresses as destinations, but the virtual router address does appear in this in the protocol messages, and we can see priority as well.
and this guy's priority 110, 23.1, 23.2, he's priority 100. So that's why the higher priority decided he was going to win, and he took over, and he stole the virtual MAC address at a particular stage. So that's curious. Aware of time, I'll skip straight to the breakdown on that then. So, got some values there that were interesting, and this is the diagram that I've started to draw from it. So we've got an OSPF relationship here. It's area 1. You can dig into what that means and what that might mean in terms of the size of the network. We can see the hosts that are involved, the MAC addresses. Again, I'm just noting down the various, very limited bits of information that I need to be able to see whereabouts things are at a glance. I can see here I've put down frame IDs. I've noted their preempt at frame 24. That was whereabouts the MAC address switched over from one host to the other on the virtual MAC address. Interesting. And then when we look at the HSRP values, there's some different things that we might have cared about there. So over here in OSPF, there's no priority that was specified. Well, there was, but it was 1. And it's not relevant to us, but we can see other information here about designated router IDs too. Digging into the packets, that's curious information. Those addresses don't tie up with what the physical addresses we saw on the wire were, or the IPs we saw on the wire were. So that could be curious information too. And within the HSRP packets, then obviously I pointed out we see priorities specified, and this guy 23.1 over here had the higher priority, and he took over at frame 24 as being active. When you can take a look at these other PCAPs, the LLDP detailed has got an awful lot of terrifying information in there, frankly, in terms of what you might see of a host demonstrating its capabilities. Digging into that particular PCAP, and it's 1 frame in that PCAP, so I'll leave it as an exercise to you at this stage to go and do that. But have a look in there and see what kind of terrifying information you can see in the hex view, potentially in that screenshot. There's some plain text there that might be interesting, and there's a lot of values in LLDP. There's another example there that contains some more information. I was really surprised. I'd never seen this particular feature in LLDP myself before when I was looking for this PCAP, and civic location information. It's got damn near a street address included in device information that it's sending out, which I found to be very curious. It's all kinds of information that you might see there that's either included as a default for a protocol or that somebody decided might be really interesting to include. Another PCAP that we've got in that zip file that I was looking at or link you to is this PCAP-NG example, which was created by Sarka. He has, it's not a particularly interesting PCAP, but there are some values in there. It's mainly being used as a demonstration of what values were, or what features were added in PCAP-NG versus PCAP. And actually, it's a wonderful place to go and see a demonstration of capture file comments being added and frame comments being added. There's other information in there too that is quite curious when you start digging into it. But again, just all of those views that we went into, the conversation view, the file statistics view, looking into the Ethernet layer, looking at in the frame header, identifying interface that was in use there. You can also see in the capture file properties. These are all troves of information about where things actually might be on the network, or what hardware it might be, or operating system. SMTP PCAP, which I will open quickly, because this is the one place that I thought was relevant to actually use the follow stream view. So quickly grab that one, SMTP. Close that up, find this, just find any packet in this particular conversation. Go to follow TCP stream. And as I say, SMTP, plain text. There's a lot of back and forth in this, but
the coloring makes it easy to see what's going on here, to see what kind of information we're exchanging. We can see there's auth data here, that might be curious, full addresses that are included, and then actually an awful lot of MIME data too. And there's an attachment down here. We've got all kinds of information that's thrown in here that it would take an age to discover by just scrolling through the packet window. The follow TCP stream here makes this incredibly trivial to see. Like, has this worked okay? Is the conversation actually functional in a way? It's not obviously going to tell you whether or not you've got any retransmissions or out of orders. You still need to go through and look at that. But in terms of making the actual diagnosis of what data was there, the follow TCP stream, if it's plain text, I find that quite useful. But as I say, for about 3 protocols, and getting fewer by the day, thankfully. IGMP dataset is also an interesting PCAP that exists in there. IGMP in itself is a massive topic, but this is close to my heart and would make for an interesting longer talk on its own. In general, make sure that you're paying attention to like what you're seeing in the capture that you think is useful, and remember, if there's something there that you think is useful and it's not, go back and ask for it. Go and ask, and just keep doing this, right? Rinse and repeat. You're going to get better. Oh God, what have I done? You're going to get better at this the more you do it. We only get better with practice, so do keep practicing. Clearly, I've run out of time for graphs, so I won't be doing those, but I will just take this moment to say thank you. Thanks to you for coming, because if you weren't here, none of us presenters would be here, right? So you are the VIPs of this conference. You're the future of it. You're the people that we all want to be here to meet and to talk to, and we really hope that we see and speak to you again in the future. To the speakers, like, we all learned something from you at some stage, and it's wonderful that you share your time and your knowledge, helping us all scale. And to all of the organisers, thanks so much for all of your hard work making this happen. There's a couple of people in particular I just have to say thank you to: Tali, Sherry, Angelo, Jasper, Christian, Janice, and Gerald. You've all had some small role in me being here today and in all my previous instances here. There's a lot of good people here at SharkFest, and I hope you found a community, and I hope you want to come back. And so, again, thank you to you, and thank you to everybody at organising SharkFest. Thanks, and I'm done.